Oi, mitigating frequency bias and anisotropy in language model pre-training with syntactic smoothing. Interesting paper today. They do some stuff with messing around with token embeddings and making them train even the rarer ones that are not being trained very often. This paper is cool in the sense of I think it's good inspiration for some potential future avenues, even though a raw implementation the way it's currently done here is not ideal. The results aren't like actual blow your socks off or anything, and the decrease in efficiency from memory being taken up is not good, obviously. But in the reading today, in the video, I go over my idea for how I would improve it in a way that I think possibly would actually give some good results that are worth the computation increase. So yeah, let's get to it. Before we start, remember to like, subscribe, comment, share all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, support me either through Patreon or YouTube. For as low as $1 per month, you can get early access to my videos, or for a one-time payment, hit my Venmo. And if you'd like to borrow my brain for an hour or two, book a consultation call. All links are over on my Linktree. Let's get started. Humans possess a remarkable ability to quickly understand the meaning of unknown words given contextual cues, and language models struggle a bit. Because language is characterized by a Zipfian distribution, which basically means that they are exposed to frequent tokens exponentially more often than infrequent ones during pre-training. It could be the case that like frequent tokens are just like 10% more common than infrequent tokens, but no, language is such that like rare ones are exponentially rare, right? Consequently, the representations of these frequent tokens are optimized based on exponentially more learning signals than those of low frequency tokens. Infrequent tokens are pushed into a narrow manifold. Because of this, infrequent tokens are pushed into a narrow manifold of representational space, right? So actually, all tokens are pushed into a relatively small manifold. This concept is called isotropy versus anisotropy. So basically, if we imagine that a model has two dimensions and therefore every embedding can go on the x and y axis, right? Then what we would want in theory is to have the model's token embeddings as vectors be evenly distributed off in every direction. We do not restrict norms, at least with RMS norms. So you would expect something like this, right? Of like have the arrows go in all given directions, have them roughly spaced out evenly apart, and that would allow you to take advantage of the entire representation space, right? What actually happens with the embeddings of models is you end up with the model choosing, let me use a different color, to put everything into a small restricted area of what it totally potentially could. And so you end up with all of these vectors in this restricted cone, right? And the blue vectors are isotropic. The green ones are anisotropic, meaning they are not taking up, they are not the entire representational space, they are not evenly distributed, they are instead clustered together, right? Language models in general have this issue of all their embeddings are clustered this way, and you don't like that because it means that you are not taking advantage of the entire representational space, and where if you could have in the beginning, you would have just given the model fewer dimensions, aka had a smaller, more efficient model, right? Whereas what models actually do is the green arrow, they'll cluster together. You end up wasting tons of your space to compute in, right? And beyond that, for happening to all vectors, what we actually get is for especially rare tokens, we'll call these the purple tokens, they, even worse, cluster up especially bad into their own little group of rare tokens, as opposed to the rest of them are still close together but relatively more evenly distributed. All the rare tokens, the especially rare ones, cluster crazy close together, and the model just kind of treats them as all the same thing. It doesn't have enough data to actually get serious semantic understanding, and instead just puts them all into the same area and says these are all effectively the same thing. They are just rare tokens that I don't know what they actually mean, but they are rare enough that I'm just going to treat them all the same, basically, right? And the idea here being that separation in embedding space corresponds to actual semantic similarity or difference, right? Now, in this paper, they propose syntactic smoothing, a syntactically guided label smoothing approach to improve the representation of infrequent tokens in language models, with the hope being that they stop all clustering together like that, right? And that the model learns more semantic information about those tokens and then can use them better downstream, right? The data set of note is called BLIMP. It comprises of 67 data sets, aka subtasks, each consisting of 1,000 pairs of grammatical and ungrammatical sentences that differ only with respect to a specific linguistic characteristic, covering syntax, morphology, semantics, all of the linguistic terms, right? Language models are tasked with assigning a higher likelihood to the grammatical sentence, right? Now, BLIMP is carefully balanced to ensure individual tokens occur equally in both sentence types. However, within a single pair, of sentences the model is asked to pick between, there may be an imbalance in average token frequency. For instance, the sentence, Grace's piano teachers are known, has a log frequency of 8.35 on that known word and is also grammatically correct, while its associated minimal pair, Grace's piano teachers are replied, has a log frequency of 6.2. So the second sentence is both grammatically incorrect, and also that word replied has a lower frequency in the actual data set. We do log just because frequency itself is very, very large numbers, so we log it to make it all same-ish scale, easier to look at. We hypothesize that despite the minimal difference in BLIMP pairs, models trained in a typical manner will be biased by token frequency when determining grammatical acceptability. Meaning, the model, when choosing whether the sentence 1 with known or sentence 2 with replied is the correct one, might not actually be using its understanding of the grammar of the syntactic knowledge of the word known. It might instead be using just the fact that known is more frequent in the data sets than the word replied is, right? In which case, we often hear the critique that these models are stochastic parrots. That would be an example of stochastic parrot right there. It is just using statistical heuristics, aka just the frequency of the word in total, as opposed to any actual internal representation of the structure of language, right? Our goal is to quantify how language model performance differs between BLIMP pairs with large positive frequency differences. So pairs that have very big difference of frequency, we want to characterize how models act in those scenarios, and with large negative frequency differences, aka imagine if the bottom sentence with less frequency was correct grammatically, or so imagine if the sentence with less with that's correct, imagine if the sentence that is grammatically correct had a lower frequency than the sentence that is grammatically incorrect, which had a higher frequency, right? In that scenario, you would expect the model to be biased towards the incorrect answer, even though it might actually internally have built some algorithms to know the correct answer in terms of syntax and semantics. But because of next token predictions association with just like highest likelihood, highest frequency, it, even though it knows the correct answer internally, it says the incorrect answer just because of prioritizing its stochastic parrotness over its actually learned the truthness, right? First, for each BLIMP sentence pair, we calculate the average, aka we just use natural log, right? Frequency of the differing tokens. Frequencies of individual tokens are computed with respect to a model's training data, right? So we look at the training data set and we just grab every single word, every single token in there, and just count it up, count them all up, and then just take the natural log to make those huge numbers more reasonable, right? Sentence pairs, so the two sentences from earlier, are then ranked by the relative difference in these average frequencies, where positive values indicate higher average frequency for the acceptable sentence, right? So in this earlier case, the correct sentence had a higher log frequency, and the incorrect sentence had a lower log frequency on their words of interest, right? So we take 8.35, subtract by 6.2, end up with, what is that, 2.15 is our different score, right? And if instead the first number, the correct sentence, had a lower number and the incorrect sentence had a higher number, we'd have a negative value, right? Then we compute the BLIMP score using pseudo-log likelihood for blimp pairs in the upper and lower thirds of the relative frequency difference distribution. So let me show an actual display of that. Basically, when we take that difference, when we subtract by the correct sentence frequency from the incorrect sentence frequency, we get a distribution right here that roughly clusters around 0, right? And we look at the top third versus the bottom third. The top third is the correct answer is also more frequent than the incorrect answer, and the bottom third is the incorrect answer has a word that is more frequent in the data set than the correct answer, right? And now we're going to look at performance on does the model choose the correct answer or not according to these two different parts of the distribution. Now, we then define a model's frequency bias as the difference between the two blimp scores of the top third and bottom third, right? So on the top third, it'll get a certain blimp score. On the bottom third, it'll get a different blimp score. And we say it has a frequency bias according to the difference in those scores. And you see here, you would assume the model would do better on that higher frequency difference, right? Because the correct answer happens to overlap with also the more common word answer, and therefore any type of internal actual good algorithms would combine with any internal stochastic parrot algorithms to both get the same answer. Whereas on the red area, the bottom third, they'd actually be fighting each other. Is any internal sense of actual knowledge of the word syntax and semantics would be fighting the model's tendency to be a stochastic parrot and just repeat the most common word. And they find that these language models exhibit a frequency bias as high as 13.7%. That's a lot of actual performance being left out on the table. Their goal is to develop a model that can attain a frequency bias close to 0 while attaining a high blimp score. That is, a model that makes determinations on the grammatical acceptability of sentences based solely on relevant linguistic aspects rather than relying on possibly misleading statistical artifacts of the training data, right? So in this scenario, they're going for a model that performs as well or better on blimp while also not having this frequency bias. And even if it performs just as well, you now know that its performance is based off of actual syntactic understanding as opposed to being a stochastic parrot, right? So the things that it has, or the specific cases that it has success or errors on, will be actually better ones for it to do so. That'll be more resembling its actual knowledge, right? Which means that probably downstream stuff of the rest of your prompt will also do better, I would guess, even if you have a same blimp score as opposed to a higher blimp score. They propose at each learning step to backpropagate the learning signal of a target token to all other tokens serving similar syntactic roles. This benefits infrequent tokens that appear less often in the training data. What does this exactly mean, though? How do they actually do this? So first off, they consider two tokens to be similar if they have a similar distribution of part of speech tags in the training set. This is a one-off pre-processing step over the entire training set. Basically, they get part of speech tags from some Python package, I believe, called NLTK, which just assigns each word in the training set to one of 12 universal part of speech tags. This only works for English, I believe, and those tags are based on its given context, right? So every single word gets labeled as either noun, verb, adjective, pronoun, etc., right? And we have here, for example, the word blind and the word the being in blue, blind being in red. They get these labels of what percentage of the time that word shows up in the data set does it count for that part of speech tag, right? Then we tokenize the training data into subword tokens, so regular byte bearer encoding or whatever, and assign each token the part of speech tag corresponding to the word it belongs to in each instance. So one subword token could actually correspond to multiple full words, right? And those different full words could have different labels on all of their parts of speech, right? Different frequencies of them, right? As words can take on a different part of speech depending on the context, we count the number of times each token in our vocabulary appears as each part of speech tag in the training data, producing a 12 valued vector, 12 for all the different parts of speech. The result is a matrix of vocabulary length by 12. That in itself is not a huge memory drag. In this pre-processing step, I'm totally cool with any pre-processing steps computation-wise, that's fine. And so far, This V by 12 matrix is also pretty small in memory. That's fine too. And then finally, we can compute the similarity of two tokens using the cosine similarity of their part-speech distributions of this actual matrix, right? This computationally is less enjoyable to deal with. Now suddenly we have a new matrix of size vocab length by vocab length. As you all probably know, the vocabulary length of models is getting increasingly large, even for small models. I believe like Gemma 2 billion, 9 billion, etc. have like 32,000, 65,000, 256,000, like huge numbers of tokens. This is actually a significant downfall, potentially. I haven't done the actual math on this, but like I believe the significant downfall of this method is you now have to hold in memory this terrible matrix that is probably worse than the actual in any one given attention matrix. And given how big an issue quadratic is, assuming that your vocab length is longer than your maximum context length, which it probably is, this is a huge memory drag. And there's this issue with methods being proposed nowadays of, yeah, sure, your method improves things, but if it requires more RAM and more computational power than the improvement's actually worth, then it's not worth it, right? Like I would rather take a method that hurts the actual intelligence and output of the model, but massively increases the compute efficiency, because then I can just build a bigger model, right? And that like overpowers the method hurting the actual results, right? There's a very fine line trade-off happening here, and my guess is that this is probably not worth it, is my guess. So then when it comes to the actual loss function, right, what's happening in the actual loss function? So instead of a one-hot encoding, the target vector becomes a distribution across the entire vocabulary with some of the signal on the correct label J as normal, as with one-hot encoding, then the rest of the signal distributed across all other tokens according to the syntactic similarity metric, right? So we have our, for a given one-hot, instead of grabbing an actual one-hot, we look at that token and we say, okay, what is the similarity score of that token to all the tokens? And then we actually give a little bit of the probability vector of the one hot over to all of the tokens. And we basically have a token that is not a one hot. It is instead like a 0.8 on one token and like a 0.001 on like a dozens, hundreds of tokens, right? And we decide how much to distribute, how much the loss to distribute to those other tokens based off this smoothing parameter alpha. And if you set alpha equal to 0, it's just standard regular cross-entry loss, maximum likelihood, obviously. Now we also investigate the use of a pacing function that linearly decreases alpha so that at the start of training, the majority of the signal is propagated to other syntactically similar tokens, and by the end of training, nearly all of the error signal is sent to the correct token to ensure that the model still optimizes perplexity, right? That's interesting to do, is to say, okay, just beginning training when the model doesn't actually have much meaning, much semantics encoded. Let's just optimize for or for syntax, for part of speech. But then as training goes on, the model should in the end be good at the actual token prediction, right? But that does reintroduce the issue of frequency bias towards the end. They do, of course, scale those scores by temperature. Again, hyperparameter here to put it back to an actual usable distribution that adds up to 1 on the one hot, right? And the experimental stuff they used is a data for the baby LM challenge. So not perfect here, but I think fine for an experiment in my opinion. The data set was constructed to be similar to the input received by children. 56% comes from the transcribed speech and 40% comes from sources intended for children. So really a fun data set in my opinion. And then they have a small 8-layer encoder style Roberta model. And for the results, they find that their method does in fact reduce frequency bias while retaining strong language modeling capabilities. The models with the lowest frequency bias also demonstrate the lowest anisotropy, which in theory is useful. Here's that actual table. We have our base model. Label smoothing is a different method that you can consider a different comparison base. And then syntactic smoothing, their method. Low versus high is just a different level of that alpha hyperparameter. And then paste means over the course of training, it does decrease to 0 and we get back to regular next token prediction with one hots, right? And the results are a bit over the place. We do find that it successfully does decrease the actual bias, the frequency bias. That's great. And we also find huge decreases in anisotropy, right? In terms of performance itself, overall, yes, it seems to do sometimes better, but it's also like if you run 5 different models compared to one model, like what are the odds you do better on 4 out of 5 of them? It's not really like great results here. The thing I like here more so is the beginning of a methodology. The results aren't that amazing, but I would love to see a version of this that is not syntax based, it is instead semantics based, right? Where you're distributing based off semantic similarity. Trouble being, well, the model starts off with no sense of semantic similarity, so you need some kind of preconceived thing. It might make sense to use a similarity metric, a similarity matrix, like the one they have, the vocab by vocab length metric or matrix. But instead of using syntax, I think it'd be very cool to instead use like the semantic embeddings of a pre-existing well-trained model. Like grab the token embeddings from Llama 3 or something and make an equivalent semantic similarity matrix here, and then try this again. That could be very interesting in my mind, to see how that affects things, as well as linearly interpolating between that initial version with the llama model and maybe the model you're training its own embeddings. And then so as the course of training, you slowly convert over to using the model's own uh, similarity metrics for your effect and loss function. Another point about efficiency here going on is that your one hot encodings and your cross entropy loss, uh, batch size by sequence length by vocab length tensor are a huge portion of the actual memory being taken up in these models. And I don't know if it's common practice. I believe it is. I saw a paper on it recently where you can actually massively decrease the memory of that final output matrix if you take all of the many zeros in it, which is most of the data. Remember, it's one hots, right? And you just never compute them, and you can massively save on actual efficiency with your memory during training. And this method here destroys that. It makes that impossible to do. You might still be able to do some kind of like top K semantic similarity, and that would bring it back, and it is still usable. But overall, this is a second knock on this paper for just efficiency wise, is you are forcing yourself to stick into using that final output tensor of that humongous size, and you have no way to actually limit it down. So, and again, given like the lackluster results, I'd say The main reason discuss the paper today is not for do this right now. It is for this using the loss function this way is an interesting beginning to how can we actually switch from syntactic to semantic, and might a semantic version of this be much more performance? I think so. Is it performant enough to be worth all of this? Not necessarily, maybe not, but I'd be curious to see. I would love to make this into a semantic similarity matrix, and then instead of syntactic, and then do a top K on the actual similarity scores such that we can still not compute all of the zeros in our remaining K hot encoding, right? That would be interesting to me. Notably, and expected, they do find that frequency bias and anisotropy are correlated. I already knew that, as you saw earlier with the whole drawing I did with the rare tokens are in a certain place. Rare tokens are especially anisotropic, and it is also evident that the pacing approach reintroduces frequency bias towards the end of training as the degree of smoothing is linearly reduced to 0. So that whole thing they did where they like linearly decrease that actual alpha parameter to put it back to regular next token prediction is definitely not worth it. It just reintroduces the initial issue, and now at the expense of all this extra memory, right? Now, all of the syntactic smoothing models, as well as the label smoothing models at a different baseline, achieve better BLIMP scores than the baseline model. But again, the BLIMP is just one metric. It's not an actual full-on test of language models, right? These results suggest that methods that smooth label distributions, whether through a syntactic prior or a simpler uniform smoothing approach, which is what the other baseline did, which was just way too simple, enhance representation of all tokens, including the more frequent ones. None of the syntactic smoothing objectives result in a substantial performance degradation on these natural language understanding tasks, and in fact, note that for some tasks, such as whatever those are, the smoothing models yield uniform increases in performance. So there's performance increases. Again, not quite a worth it amount. In my opinion, I think it's a future version of this technique that shows promise, not this technique itself. But anyways, I enjoyed it in terms of inspiring creativity of like seeing different ideas. Hope y'all did too. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below. For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.